Thanks, John. Okay, good afternoon again. So I'm Matthias. I'm a CEO and co-founder of Navasto and an engineer. More specifically, an aerodynamicist. So you're going to note in a second that a lot of the stuff I'm talking about is on external aerodynamics. But I'd like to ask you to think about the technology that's in the back end more than about the use case I'm talking about. So I'm doing machine learning and deep learning, aka AI, for engineering for about a decade now. And during this time, I've encountered several things again and again. And in this presentation, I'd like to unpack what we mean with AI-accelerated engineering on the one hand side, where we're doing it, answering 3 specific questions that I get over and over again. Specifically, how accurate are results? How much data is needed to make good trained models? And lastly, how can we make sure that only valid predictions are being actually used for engineering decisions? And they're gonna throw in some optimization and generative AI slides in there. Okay, before I do that, I wanna start with a quick introduction of my company for all of you out there who don't know us. We were founded in Berlin about 10 years ago. Started with 2 engineers, have grown to about 20 engineers, AI scientists, programmers. And we have developed a product, a machine learning and deep learning platform, an API solution, based on our experience in working for the automotive industry, and a solution where we decided some years ago to go for usefulness of the application more than ease of use. And this was a good decision because we ended up being used in productive processes by large OEMs, for example, Seat, Lamborghini, Audi, the Bauer Group, General Motors in the States, are using this tool to build their vehicles. We are very proud that we are also the go-to solution in Formula 1 for AI-accelerated engineering. And another example is, for example, the America's Cup team, Ineos Britannia, that use this tool to design their ships. In terms of ease of use, we've decided to collaborate with our friends, for example, at SimScale, Synera, Rescale, and Autodesk, which make this technology then easily usable for the end users, for the thousands of engineers that actually can benefit from such a solution. So before I talk about the 3 points like accuracy and data and stuff like that, I'd like to introduce the idea why we're doing it and where our vision in terms of the usefulness of artificial intelligence in engineering is. So the question is, why should we need a tool like that? At the end of the day, we're having engineering processes designed to deliver a product, like a vehicle, like a heat exchanger, in a given time frame. And to arrive there, we have the engineering processes and the engineering capability that we are having available today. So we can do this. There are nice cars out there, functioning heat exchangers, but the issue arises when we try to either do the same thing more quickly, meaning 2 examples here in terms of 2 CEOs of large OEMs of Germany that try to accelerate the development processes of the technology on the one hand side. But even there, simply with more hardware and more compute, we could arrive at a point where we can actually develop those same products more quickly. The second thing that comes in is the need for more advanced products. So to this end, I've simply thrown in the image of the SU7, aka the Porsche killer, that was just released some weeks ago in Shanghai. So everyone needs to improve the products and build more advanced products. So to that end, we also need more advanced engineering tools to simply deliver better products more quickly. So this is the underlying idea, and there are 2 ways of doing this. On the one hand side, we can accelerate the workflow, like the examples we've seen yesterday from our friends at SimScale and Synera, that simply improve the workflow part of the development. What we are doing is more specifically going into the methods side of the development process by amending it with machine learning and deep learning, artificial intelligence, to simply speed up the process. So what we do is we take geometries like the meshes, the shape of a car, and correlate those geometries with the results that we know either from simulation, so a CFD simulation, an FEA simulation, or from experiments. So we correlate the geometry with the known result from what has done before, train a model on that so that we have a 3D surrogate model that allows us then to test a new geometry against the deep learning model and get a prediction of the result that you would come out of a first principle-based simulation, but in real time. So you throw in a new STL and get out the drag coefficient, the lift, the surface fields, the volume fields very, very quickly. And the idea is to enable people to actually work in real time against a real-time capable model. So instead of people from style, from aerodynamics, from structure, meeting in a room, discussing ideas, and everyone leaving the room to run a simulation, meet back a week later, we want them to be able to test an idea against a real-time capable model and make a decision based on that and iterate within those meetings. So iterate at the speed of thought is what was the idea something like 8 years ago when this picture was created in the first place. How this looks in practice, I simply want to show you in this video. So what you see on the screen, many of you probably know Blender, the open source tool that allows to render geometries and modify meshes. And what we have done is we have coupled a deep learning model against the back end of Blender so that you can now load in a geometry, simply modify the geometry, like grabbing the mesh, and then instead of exporting it and running it through a first principle-based simulation, like a CFD simulation, you simply query the deep learning model in the back end about the performance of this vehicle, and you get the drag coefficient in this case, the flow field, the surface fields, everything that's needed to evaluate the quality of the prediction, but in real time. So this is a real-time video. It's literally like modify the geometry, click the button, 2 seconds later, you have the result here. So this is one way of using it, interactive design. Another way of using such a technology is the combination of a predictive model together with a generative model. So the geometry I show on the left side of the slide here is created with a neural network that was trained on a set of geometries. By doing so, we are including all the constraints like the brand-specific designs, like the boundaries of the design space into the model. And then we can, more or less in real time, create a new geometry, which we then test against a deep learning model, a graph neural network in this case, which gives us the performance, like the drag coefficient, the flow fields, and everything like that, so that we can then close the loop in a optimization run, like for example, a surrogate-based optimization or a differential evolution, to simply search either suitable results within a design space or find actually the aerodynamic optimum of a specific design space. Conventional way, and this is how this technology is used most oftenly in practice, is the conventional machine learning workflows. On the left-hand side of the slide, you see more or less the old machine learning workflow where someone defined the design space for a specific problem, like a parametric problem, then the simulations are run, then you train a model on that, and then you can test new ideas against this real-time capable model. What we see now more and more in practice is that we use not the conventional machine learning models, but deep learning models like graph neural networks or point cloud transformers to learn directly on the shape. So non-parametric shapes can be used as an input, and then we can take whatever legacy data is available within the engineering companies and train models that then can be deployed to the end user, to the engineers. So when they have a new challenge, a new geometry, a new set of boundary conditions, they can simply use their existing workflow, the preprocessor, and then we can check if a model is available to make a real-time prediction. If that's the case, you get your result back within seconds. And if that's not the case, we simply switch to the existing simulation workflow. The engineer gets the result anyhow, just hours later. and then we can use this existing, newly created simulation data to update the predictive model so that it becomes more and more powerful over time. So those are the use cases that we're seeing here. To realize those use cases, what we need to have at the end of the day is three components, the three components I've mentioned before. So the same use case you've seen before, this workflow, side-by-side simulation and deep learning is displayed again here, just horizontally. And we have the three components, accuracy on the one hand side. Second, we need to make certain that we know in advance if a prediction can be run with high accuracy. And lastly, we need to have something in place that allows us to update the models when new data becomes available. This technology itself is physics agnostic. Also going to talk a lot about aerodynamics in a moment. It can be used and is being used for a wide range of use cases. Our customers, crash is one example, FEA is an example, internal and external aerodynamics, CHD like the heat exchanger, acoustics, electromagnetics. The solution at the end of the day really only correlates an input with an output. Input is the shape, output is the simulation result that we know from first principle based simulation, and the surrogate in the middle is agnostic. Okay, if the predictions weren't able, if the predictions weren't accurate, then all the thing would be useless. So I'd like to show you at the end, simply a comparison back-to-back of a prediction and a simulation to make clear that the quality of those predictions is really amazing. To that end, I based this part of the presentation of a data set of the driver. It's a European research vehicle. You see the baseline on the left-hand side of the slide here and the geometric variation that went into this data set on the right-hand side. So those are the extremes of the geometry that were put in there. And we had a lot of those simulations. So in total, 500 simulations. We took a subset of the data to train a model and the remaining, something like 150 simulations to validate the model against unseen geometries. And the result of that is what you see on the slide here. So we compare the drag coefficient of this vehicle against the ground truth from CFD simulation. So the x-axis is the ground truth. This is what comes out of an 8-hour simulation. The y-axis is our prediction, the real-time result for new geometries. And everything that's on this diagonal is a perfect prediction, meaning that the deep learning model exactly reproduces what you would get out of a CFD simulation. And as you see here, we are about in the order of magnitude of an error that would come from a first principle-based simulation, so we are in the noise of what you see in such a simulation. This is, of course, not limited to scalar values, but we can also predict surface fields and volume fields. In this case, on the left-hand side, you see the result from the first principle-based simulation. On the right-hand side, our prediction. Pressure on the surface, velocity behind the vehicles. This is the way that the Formula One teams like to look at this problem. And the interesting thing about this slide or this animation is that the update rate of this video, 70 milliseconds per frame, is exactly the inference time that we have in this case for the deep learning model, while each of the simulations shown on the left-hand side of the slide take about 8 hours to come back on a GPU solver. So zooming in, simply comparing in more detail the quality of the solution, again on the left-hand side the ground truth, on the right-hand side the prediction, you see that it's very, very close to each other. Even if you look into further details, like I now plot the velocity components of this field on the screen, you see that both the location and the magnitude of the solution matches very well. And even if they put the two of them on top of each other, you find that the prediction is more or less indistinguishable from what you would get out of a simulation, just that it's real-time capable. To prove the point that this is not limited to external aerodynamics, I brought two more use cases. This one here is a crash use case. So this is the crash box of a vehicle on the left-hand side. The simulation running for at least a few hours on the right-hand side. The prediction, which is happening in about 20 milliseconds per time step. The same thing here on a full vehicle. On the left-hand side, in this case, our prediction with about 20 milliseconds per frame. On the right-hand side, several hours for the full physics-based simulation. And finally, one example, the only thing that I found within my company with relation to additive manufacture, it's a lattice structure, or a rather hyperstructure. We have done this work together with Abemis, who produced the data. You see the simulation result from FEA on the middle column, the prediction that we make. And I think what you see on the right-hand side, it is a video. I mean, this is not even measurable, the prediction time of such a simple network. Is one of the options that we see is coming out of those real-time capable models. Even if you don't change the geometry, you could test a lot of load cases very quickly to ensure, for example, the robustness of a specific design. Okay, now this part was at the end of the day about, is it possible to train machine learning models and deep learning models that are accurate? The answer is yes. We can train models with some asterisks attached here that are producing results indistinguishable from a simulation. The question is now how much data is needed. And I've shown it before, a model that was trained on 350 engineering simulations. Usual starting point in our business is something like 50 to 100 to train a model, but at the end of the day, it's really about take whatever's there to train a model and then continue to teach the model over time when new data becomes available. And I'd like to simply illustrate this based on an example of the driver you've seen before, and then I'm going to add the information of the cheddar to the same model. So, as illustrated before, we can train a model, we just take whatever's there, are able to predict the drag coefficient, or able to predict the flow field and the surface fields. Okay, now, a new data set becomes available. In this case, in blue, you see the driver model. In orange, it's the VW Cheddar. So it's a production vehicle in contrast to the research vehicle. This has an engine bay, this has an exhaust system. Both are limousines, both are cars, but they are distinctly different in terms of geometry. Now, however, if you would run an inference on the model that was trained on the driver, with the Cheddar, the output would be nonsense. Entire nonsense. However, if you now add a few number of samples, like 20 in this case, to the pre-trained model, we were able to predict new variations of the Cheddar. These are the blue dots in the bottom left corner of the plot, and still have a model that's able to predict the shapes of the driver and everything in between. So the underlying idea is here that you have a model that simply grows over time. Whenever new data becomes available, you can add this data to the model and have a growing model within the corporation that's fed by every simulation engineer that is using a simulation workflow. So the 2 points were now accuracy and amount of data required. My last point I'd like to make is how can we make sure that only valid predictions are used to base engineering decisions upon. There is no analytical way to quantify the error of a machine learning or deep learning prediction. We need to make some metrics available, nevertheless, for the engineers to judge if they can base an actual decision upon this prediction. And to this end, we are proposing to do two things. The first thing we usually do is we compare the new challenge, the new problem, the new geometry, to everything that has been used in the training before. So on the left-hand side, you see, again, my driver vehicle, now with a morphing roof height. Everything that looks like a normal car was part of the training data set. Everything that looks like a flat thing or, I don't know, like a van was not part of the training data. And what we then do is we simply compare the new shape and the boundary condition with the data set that was available during the training, and we can then tell the engineers if they are running interpolation or extrapolation. Interpolation works like a charm, like you've seen before. Extrapolation is definitely luck involved. So usually we have something like a confidence value of 0.7, 0.8, where engineers are able to use the prediction. For everything else, they're required to run a simulation. So it's the one thing we can do. Another thing we can do is we can use the statistical properties of the machine learning and deep learning model to also compute local uncertainty within a model. So on the left-hand side of my car, you see color-encoded the uncertainty that's coming out of the machine learning model. Different variants available, multi-head networks, deep ensemble averaging, dropouts, whatever's available in the world of machine learning and deep learning can be used to not only get a average value, but also some form of standard deviation or distribution of data to estimate the error. So red means the model tells me it's rather uncertain. Blue means the model tells me I'm certain. So this is an information I get without running a simulation. But if we would then run a ground truth simulation, meaning I simulate the thing and subtract my prediction from the actual value, I get an error on the surface here. Red again meaning high error, blue meaning low error, whatever the specific error is. You see that my initial uncertainty estimation correlates very well with the actual error I encounter for the ground truth simulation, so that I have a set of tools to actually judge if I can trust this prediction or not. And thus, it's not just guessing if it's useful or not, but there are several quantifiable measures available to make sure that only valid predictions are used to base engineering decisions upon. With that, I actually want to close the presentation. I hope it was somewhat useful. If there are any questions, I'm more than happy to answer them.
How many input nodes do you have on your model?
That absolutely that depends on the GPU that you have available. So in practice, we are working with something like 1 million or 2 million nodes on the geometry. Million. Think about a Formula 1 car. Formula 1 car, you need to represent the entire geometry with all those wings and vortex generators.
So every coordinate point is input.
Yes.
Does the mesh need to match before and after when you train?
No. This method, there are different methods. Like a GNN, like a point cloud transformer. Those are invariant. No, the mesh can be arbitrary in the input. Does it make sense? No, that's not to be. This is in production. This is not research. We are selling this. Thank you. It's really good.